the ability, if you think about the underlying process, how you can really transform how equipment works, is something that we don't think about much in the coarser mineral processing side. If you don't do it at the fine end, you're sunk. So really, I think we found this interesting, taking the finesse of finer grinding upstream into the coarser grinding, I think is of great value to us. So thank you, Arno, for agreeing to present for the GCC seminar as our super fine guy.
Yes, thank you very much, Malcolm, and also thank you very much, Marcelo, for the nice introduction. And hello, everybody. So good morning, good evening, depending on where you are in the world. Yes, they asked me to give a presentation, and I thought maybe it will be not the last, I guess, in this GCC seminar. I said maybe the first one could be some overview about what we are doing. So there's some new work just published, but also some older work. And so as the main purpose, I think a main idea behind the presentation was to show you some examples how to the stress model, what was developed here, can be used, you know, to really optimize mills, to understand the operation mode of mills, and maybe also to design new mills. And I think more work, or this more on maybe a single particle stressing, more on population balance modeling and so on, that maybe I will present in the future, mostly also connected with this stress model. So that means today I want to say a few words. I think it's not something special, but as an introduction to energy efficiency and production capacity. Then I would like to present shortly our mill-related stress model, and then how this can be applied for scaling rotary impact mills. That is a work by Michael Junke together with some students of us. And then we come to the product-related stress model, and also I have two examples there how to use this one. One is for what we are almost always doing, using wet stirred media mills, you know, and predict the result. But also I want to show you how to optimize dry ball milling processes. It's more or less also a stirred media mill in this case, but we also have done some work with normal ball mills, or we're doing it very intensively in the moment. But I think the most complete results we have for this vertical ball mill with a stirrer. And then I come to the conclusions and the outlook. Now, start a few words. Sometimes, I mean, it's not so much in mineral industry, but in other industry, it's important to explain why it is really important to increase the energy efficiency, and that means to decrease the specific energy consumption. And it's not only because we want to have low energy costs, you know, it's also because if we keep the power consumption or the power input of the mill the same, we can have a really high production capacity, like shown by this equation here. And on the other side, we can have less contamination of the product by wear of, for example, grinding media or the mill shell, and also by that less wear costs of the machine, and by that again more or seldom, that means less stopping of the grinding plant, and that is more or sometimes much more important than lower energy costs. And also, if you have maybe organic product, you have less issues regarding cooling. So what is the energy doing, or what is the flow of the energy from the motor at the end to our product particles? You know, if we put the energy into the motor, first of all, some of the energy we lose in the drive system. Usually we measure that by the so-called no-load energy or no-load power. It's called here energy, but usually, you know, the power, the motor is given some power, but power times time is energy. And so this is something what I think very often is not really looked at, but maybe from the machine supplier side, that should be also something what can be optimized in the future to decrease our CO2 footprint. So that is then the energy which is really going into the mill chamber, and this energy which is in the mill chamber now is not only used for really stressing the particles. A lot of the energy especially in fine grinding, is used for the transport of the product particles, for resistances. Let's see, also friction inside the chamber, and also maybe deformation and wear of the parts of the machine. So only a certain part is then really transferred to the particles. And this part, for example, in a yaw crusher is much higher than in a mill, or an impact mill or something like that, where we have very small particles. And then the question is how this energy, which we really transfer to the particles, can be transferred into a fine product with very high surface, specific surface, for example. And that's something where I want to talk about mainly how we can transfer this energy, what is described in this case by an energy transfer factor, which also can be optimized. That means maximized times the energy which we have inside the mill. And this is really the energy which goes to the particles. But how can we use this energy to get the maximum product fineness or the maximum product quality what we want to have? And that is the main goal of using the stress model, what I want to show you in the next 40 minutes. And very important is the stress intensity, because this stress intensity decides about how effective we can use this energy. One example, there are a lot of old results, so that's not new, absolutely not new, from Schöner, Schubert, and other colleagues also, in King and so on. They measured single particles with different stress intensity by compression and also by impact. So Druck means compression, power means impact. And you see that the energy utilization, what is the energy as a specific surface increase divided by the energy used, that it is higher for compression than for impact, and that it depends on the particle size. So stress intensity and also on the stress intensity. So energy utilization depends on the kind of stress, the stress intensity, and also the particle size. I think this is something what is a very basic and important start. And then I come to the mill-related stress model. And what is important, what I want to say is that this model is not only valid for wet stirred media mills, where we used it mainly, but I think this model can be used for all kind of mills, because every mill has something common, and that is that we have individual stress events, and in this stress event we stress particles with a certain kind of stress and also a certain intensity of stress. So that we thought it can be a really simple model experiment. We have one particle, we have a hammer or something like that, and then the question is how we stress the particle. Do we it with a high energy or low energy? That means small or large hammer. Do we do it with a low or high speed? Also this changes the energy. And also, do we only do that once, or maybe more often, maybe also with less energy than for one particle? And all that decides again at the end about how efficient we are in our comminution process. To have a closer look, we said maybe we should have two different looks on the process. One is from the mill. That means what is the hammer doing, or what is the mill doing? How often we stress a particle. That means frequency of strokes or stresses. And how strong are the strokes? That means the force or the energy, in this case of the hammer or inside the machine. And on the other side, it's how we do that, or we have a look on the product. So what is coming out and what is the stresses acting really on the product. That means how many stress events have a certain mass of product achieve, or what is the number of hits on a certain particle and their the fragments, and what are the intensities of these hits. And that means intensity means always energy per mass of particles which are stressed. That means something like the specific energy in a single stress event, and that we call product-related stress model. So coming first to the mill-related stress model, and I think most of you know that. So we said, or others said, like Schöner, I think already started, that type of stress is very important. then the stress frequency, how often some stresses or stress events are acting in a mill. For example, in your crusher, it's very seldom. In a rotary impact mill, it's very often. And then the stress energy, that means the energy which we can provide to the particles. So this is independent on the size of the particles and the material we have in the mill. It really describes only the operation of the mill. And the best what we can do is we can use a frequency distribution or also a cumulative distribution of the stress energy to describe the behavior of such a mill. And that is such a model distribution. You have a frequency distribution of this stress energy. So it's in this case normalized frequency distribution. And you see that we might have a lot of stresses with less stress intensity, or in this case, stress energy, sorry. And then we have also some stresses or stress events with high stress energy. And there's somehow a certain maximum stress energy. For example, if the biggest ball is falling from the full height to the bottom in a ball mill, then we come to the maximum stress energy. And this curve describes really every mill, or can describe every mill. This challenge is to get it for every mill, to derive it. But I will give you some hints what we can do, maybe also without knowing exactly this curvature. For example, sometimes it's sufficient to use a maximum stress energy to describe the mill behavior, but we more and more go to have a more or less characteristic value, what can be something like the mean stress energy. But at the end, if we want to model it correctly or in detail, maybe we also need the entire curve. So when we now know the stress energies, and then how is it related to the specific energy, and there we derive this equation. I mean, it's also simple that we say, okay, the sum of all stress energies give us the overall energy which is transferred into the grinding chamber. And if we relate that to the mass of the product, or this is the energy which is transferred not only in the grinding chamber, but to the particles inside the grinding chamber. And if we then translate that to the mass of the particles, we come to the specific energy which is transferred to the particles. So that's not the specific energy which is put into the grinding chamber or delivered to the grinding chamber. It's really transferred already to the particles. And as I have shown before, this is then related to the specific energy which we transfer into the grinding chamber, or we deliver into the grinding chamber by this energy transfer factor, we called it. After a long discussion with Mr. Schönert, who was my one of my PhD supervisors, so that was then the name we defined for that. And so the product of the number of stresses and the mean stress energy can also be used for the sum of the stress energy. So at the end, it means if we know the stress number, if we know the mean stress energy, then we can almost, or then we have also a constant specific energy which is transferred to the product particles. And if this transfer factor keeps constant, then also delivered to the grinding chamber. Okay, and now how can we use it? And there's a sample. I think I like this example because it's really relatively simple. So Michael Junke from Novartis, I think maybe some of you know him. He is, I think, gave also, for example, a plenary lecture in the, I think, ESCC last time, or at least in our purpose, but he is also very active in the comminution field. And his purpose at his company was, how to come from small mill devices, how to predict what is the result, or how to operate the large production mills. Large for the pharmaceutical industry, it's very small for the mineral industry still. So the question is how to do that. And so his idea, so there are more results, but to show that it's not so easy, but first he had to look at the different rotors. So that is for the large production mill, then this is the pilot mill. This was the first design, and at the end we come to this design. I will show you results first of the first design, and this was a new mill, very small one, what he wanted to, from here he wanted to scale to the production line. And this was the first design. Previous study means, in this case, I will show you the results of this previous study, and then we come to this final design. And the first idea was, it's, for example, working in some cases for the stirred media mills to use the maximum stress energy that can be calculated by knowing the kinetic energy which is achieved on the particles. And if you divide this by the mass of the particles, then it's coming to, it's more or less the stress intensity here already, and not the stress energy. Sorry, because I copied it from him, but it would be here in correctly. It's already the stress intensity, because the mass is it's divided by the mass is divided by the mass, and that's why it's not in here. Okay, this is the maximum one, and then we tried to correlate the results, but he didn't get a good correlation. So there were big differences between the different mills, also between the different throughputs. So that was not sufficient. So then that means we need a better description. That means we need the full curve, so the full stress energy distribution, and but then he calculated a mean value from this full distribution. So he counted the pins, and then he calculated the stress energy for each pin, or multiplied it by the stress energy for each pin, and then he come to this, let's say, mean value or cumulative value for the stress energy. And with this energy here, then correlated the curves, and now there were a much better agreement. So if we have this mean stress energy, but then he said, okay, to operate the mill with these different stress energies, you need different tip speeds, 129 meter here, 118 meter per second, and this gives some other problems. And then he talked to the manufacturer, that's for the Calver Alpine or Alpine, and they redesigned these rotors now, so that at the end the tip speed is very similar in the three mills, at the same, to get the same mean stress energy. And with that, then you get even much better correlations for the three mills. And now he has a really nice tool, to run with a very small mill, but can predict for larger mills what happens. Okay, coming to the product-related stress model. In this case, what I already said, we now relate the frequency of stresses to really a certain particle, and then it means we have the stress number per feet particle, and we relate the stress energy to the mass of the particle, or force to the area of the particle. So we come to the stress intensity. These are two related characteristic values, but also again we have a distribution of the stress number per feet particle. Not every particle gets the same number of stresses, and again also the stress intensity has a certain distribution in all the stress events. But in the following I will more or less work with characteristic values for that, and the stress intensity determines at the end, and that is important, how effective the specific energy is transferred to the product, what we have already seen regarding the energy utilization for this really basic investigations at the beginning. From that, now we can maybe make this plot, that is the product quality or specific surface as function of the stress intensity. In this case, I use the relative one. So I said there's an optimum stress intensity. I will show you later, or the next slide, where we have the maximum energy utilization, and I related now the stress intensity to this value. And usually you have, first you have no breakage, and at a certain point maybe there's some chipping, and at a certain stress intensity then you get the full breakage of a particle. And after you have this point, then you get more fines usually, that is this red line, but the increase is maybe smaller than you have it here at this point. And this increase depends on the material you want to break. For example, for minerals and hard materials, usually the increase is relatively high. It's not 1, it must be less than that. But if you have really weak materials or agglomerates or, for example, yeast cells, then it's maybe very small, or in the extreme case, even 0. That means if it breaks, for example, if a yeast cell breaks, and that is what is the product quality, because then you have the internal of the cell, then more stress intensity brings not a better result. Also, what we found, and maybe it's interesting also for other mills and for stirred media mills, is that depending on the stress intensity, you also get a different distribution of the particles. I think it's also well known from basic research that if you just hit the particle with the optimum stress intensity, then you get a really tight and narrow distribution of the particles. If you have a much higher stress intensity, then you get a wider distributions. We really could find that also for stirred media milling processes with different materials. And now from this curve, you can calculate the energy utilization, because the energy utilization is, for example, the increase in the specific surface divided by the specific energy used for it. And this is, in this case, the stress intensity, because it's the specific energy for in one stress event. And then we can plot this like here, and you see that we have exactly in this point 1 where we have the optimum stress intensity, we have the maximum energy utilization, and then we have a decrease. So that means we should operate our mill maybe a little bit higher than the optimum stress intensity to have a really nice or really high energy utilization. This was also found for other materials, also from basic research. These are 2 figures I got out of the Handbook of Powder Technology, which are results from Schönert and Rumpf and also from Unland. And they all could show that the energy utilization depends on the intensity in case of an impact milling. And in this case, this is for a compression of a bed. You also get a certain maximum energy utilization depending on this stress intensity input. Yeah. That means there is an optimum that we want to find and which we want to use at the end to get the minimum of specific energy, but maybe also the maximum of throughput and so on, like I said at the beginning of my presentation. If you use this relationship, what is shown here or what is shown here, then you can also transfer that into a relationship with the specific energy, because we want to have usually the same product quality with a certain process. And that means the specific surface increase would be constant. And then we come to this equation where we say that the specific energy divided by a minimum specific energy should be a function of this ratio of the stress intensities. Now for, in this case, our stirred media mill, as an example, the stress energy can be determined by the kinetic energy of the beads, which is a function of the volume of the beads and the density. And the volume is a function of the size of the beads to the power of 3, and also a square of the tip speed. So it's an equation very simple for the kinetic energy. And this kinetic energy is usually used for the milling or the stressing of the particles, but also for the displacement of fluid or what we have between the beads, and maybe also more or less of the deformation of the beads itself. Now, if we assume, that there's no deformation of the beads, if we assume that the displacement of the fluid can be neglected, then we can say that this kinetic energy is decisive for stressing the particles. And what we have, I'm showing here is results from 4 different experiments where we kept the stress intensity or stress energy almost constant. And what we can see is that for if we want to have a certain particle size, we need a certain specific energy, even that we change the density of the balls or beads, the size of them, and also the tip speed, but we get the same specific energy. Now, if we plot the specific energy as function of the stress intensity, then we come to this plot what has this optimum curve, what I think is always shown almost. And what we want to do is now to work in this region here where we have very small specific energies. As I said, this is in this case only valid for the case that the media speed is proportional to the tip speed, that the stress energy can be a measure for the maximum energy, and that we don't need the full distribution, and that is only one particle stressed significantly. So that means the stress intensity is almost independent on the size of the beads. I think this is why we are very lucky for this wet milling. I will show you later the case for the dry milling. There we have to consider the mass between the balls, and so that is then not so easy like it was here for the wet milling. Okay, then we can describe it by such a curve on the right side. So this is no logarithmic plot, but in a log-log plot, this is a straight line, and then we can describe that by such a power function. And normally, experimentally, we measure the fineness for four different stress energies, for example, like shown here, and then we can draw this curve and can find the optimum value. Should come now. Yeah, oops. We can define the optimum value and also the minimum specific energy. This one depends on the material. What is shown here, the red one is the limestone I have shown before. The black one now here is, for example, yeast cells. And you see we need smaller stress energy because they are weaker, easier to break. And also the specific energy consumption is then lower because for each breakage we need less stress energy. But if we increase the stress energy far above the optimum stress energy, you see then we have a high slope, and at the end we can use much more specific energy than in case of limestone. If we choose poor parameters for the mill. Okay, now how to use this model. So I will now proceed with wet stirred media milling, and then I come to this dry ball milling. And I think I have to hurry up a little bit to be in time at the end. So I think for this stirred media mills, what is nice is that you have a lot of different designs. I think most of you are coming from the minerals industry. You really know the ISA mill, what is shown here. But there are vertical mills on the market also increasingly in the mineral industry, or mainly there. And also you have other very specialized mills for pigments or other ceramic materials and so on. And the question is now, what is the grinding behavior and the efficiency of these different mill designs? And you can run experiments always the time, but then also you have maybe the issue that you can run the experiment only in a small mill, but then you want to know what happens in a really large mill like this large ISA mill. So also there you have to do a prediction of the change in the geometry. And how can we do that with a minimum of experimental effort? And what we usually do is that we first estimate the distribution of our stress intensities. So that is the stress frequency for different stress energies, but it's a cumulative function in this case. And you see that from that we can define a median value or also a mean value. And this we used for describing the effect of the different mill design. If you want to do it in more exactly, then you need the full curve, and then you can do it by population balance modeling. We also have done that to get a full particle size distribution at the end. But here we will do it in a more simpler way. And we found that there's a certain factor which we, for the mill, how the maximum, or let's say how the mean stress energy depends on the mill size or also the mill geometry. If we have the mean stress energy, we can also calculate the stress intensity. We found that for very high solids concentrations, we have also to consider the mass between the beads. So then, you know, there's also not so easy that we can use only the stress energy. Okay, then usually we plot this optimum curve. Here it's maybe a different material. In this case, it's for aluminum, and like I think Marcelo or Malcolm was it said that it's really fine milling here. So we go down to, in this case, less than 40 nanometers, but I will show you later that it works for all the size ranges for stirred media mills. Then we plot, so from here you get the optimum value. So that is always in the minimum. We said, okay, that is the optimum value. This optimum value is then plotted here on the x-axis, and we said what at the optimum stress energy, what is the minimum or what is the medium particle size we got, you know. So at this point, what is the medium particle size? And then we plotted this for the different materials. We found that we get a nice correlation for zinc oxide and alumina in this case. And the question was, can we define a certain parameter so that we are always on one line? So that means that we can calculate in advance what is the optimum stress energy. And Sandra Breitung-Fäß, she had a look, and you know, we did some work together with Poikat on the grinding limit, and we found that this depends on a size x min, we called it, and this size x min depends on some other material parameters I show you on the next slide. And also what can be estimated that it depends somehow on the global compression strength of a material. So if it's really large, you know, not depending on the size in this case, and on the size of the particle. So that we said, okay, the work or the energy which we transfer to a certain particle divided by the strength of the particle is a stress energy divided by the volume of the particle and the density times the density, but we simplified it. It's a proportional sign here, sorry. Exactly, and then times 1 divided by the strength of this material, and this is always the stress intensity divided by the strength. So that means how much higher is the stress intensity compared to the strength of the material, and this was a function of the x50 value divided by the x-min value. This x-min value is the minimum particle size which can be achieved. That depends on the shear modulus, on the Burgers vector, on certain materials constant, and what was done, you know, in this joint work. There's a publication where you can have a look at it. And then we plotted this all these materials from alumina, zinc oxide, silicon carbide, silica, silicon nitride. So it's hard materials. But later on, you will see limestone, for example, also fits very well. And you see that they are all on one line. Here we have stress intensity divided by compression strength. And here we have this current particle diameter, x50, divided by the minimum particle diameter. And this is a nice correlation. But for us, it's better to have the strength on the other side. That means this one was then shifted to the other side to determine the optimum stress intensity. And this is this curve. You have the optimum stress intensity as a function of the, let's say, maximum global strength of the material times this minimum value, the power of 3, divided by the size what we want to have to the power of 3. And if we plot that, we get this straight line. So it's somehow a global curve for. And also, if we calculate the right stress energy in distribution, then we can use it for different mill designs and mill sizes. Okay, so that was very nice. So by knowing the material properties, now we can decide what is the optimum stress intensity. And this should be not only valid for stirred media mills, it should be valid also for other mills, but we haven't really checked it. It's something an ongoing work. And this compression strength, we found that we can use also to estimate this minimum particle size. it's only an estimation, you know, very precisely. Then you have to also get all the material parameters I showed you before. But from first estimation, I think this line worked nicely to get this X min. Okay, then we have that was one, let's say, very nice curve, and then we thought about, for this optimum stress intensity, we should need a certain number of stresses, you know, to come to a breakage at certain fineness, you know, normally maybe only once. And this turned out also to be a nice correlation. So depending on this optimum stress intensity to achieve a certain fineness, so each optimum stress intensity means also a different fineness at the end, you need a different number of stress events, you know, and this was also one line for different materials and different mill types. So we have two master curves, maybe we can see, and with this and with this master curves, then at the end we can calculate the stress number for a new operation mode or operation point. So this is the breakage number for the optimum point. This is the optimum stress intensity, and this is then the stress intensity for the new operation point. So how we can use this equation? So we can first determine this optimum stress intensity, like I've shown you by this curve here, with some more points in this case. And based on this overall strength and so on, so one direction. Then we can use the second master curve, you know, to determine this breakage number for this optimum point, and then we can put in, you know, the stress intensity what we want to have a look at, and we need still this factor alpha, so the power of this equation, and we found that this depends on the Young's modulus. Otherwise, you have to run an experiment to find that out. With this stress number now, I cannot show you everything because then the time is over. We can now determine the stress. We can predict the grinding time and also the specific energy consumption. That is, this procedure is shown here. First, we determine by the geometry the stress energy distribution. Then by the material parameters, we come to the master curves, can determine the optimum stress intensity. By that, we can get the number of stresses we need. And then we can calculate the grinding time and also the specific energy consumption. What is shown here, for example, for an isomill, it was a first experiment with the isomill M4. We don't need it, but we wanted to check. So the curve is also valid for this mill type and the coarser limestone in this case. Then we can determine the breakage number, or the number of breakage, the number of stresses, like with the second master curve, and then we can determine here the grinding time by this correlation. And this was really in line with the experiment, and this is the M20, so we didn't make the experiments or use the experiments here for the prediction. It was only really calculated and only based on this master curve. And then we have the M20 results really nicely. And also we can predict the specific energy consumption, but then we need some information of how effective you know, the energy is transferred to the grinding material by the beads with this factor, and also if there is some damping, but it would be too complicated now to explain how we did that, but it works. Okay, now coming to the end, and I want to show you maybe for me the nicest example, optimizing of dry ball milling processes. So we really do that for normal ball mills in the moment, but Anderson Chagas, who's doing it, he's coming, that's I think a really nice GCC example. He's coming from Brazil, from Marcelo, did his master there and is now doing his PhD with me, or in my group. And he's doing a lot of dry ball milling optimization and modeling. But I show you in the following more. It's on stirred media mills, what has been done by Paul Chivara. Maybe some of you know him, but he is now in the industry working with stirred media mills, but now with wet stirred media mills. And what he has doing was, you know, also to have a look on dry stirred media mills and how we can optimize them, but also how we can predict the fineness of different operations of these mills. And but up to now, when you started, there was a poor understanding what really happens in such mills and what are the stress conditions, how are the power transferred to the material, and so on. And we started with this smaller batch-wise vertical mill. Then we had also some investigations of the sub-processes, what happens really between the beads, and at the end we come to a pilot line or pilot scale closed circuit grinding. I think because of time I skipped this in my presentation. I only wanted to show you, the results with the vertical mill, because it's really nice to show how the stress intensity has to be calculated and how we can use this also in this case. So for different tip speeds and different, in this case, grinding additives, we can get different results. So this is one grinding additive, epanonic acid, and depending on this grinding additive, we get different flow properties. So that is shown in the next slide. If you use a different one, the glycol, in this case, we have a much higher particle size, so we need much more energy to achieve the same fineness. In this mill, in another mill, it can behave different. So the powder flowability is very, very important. And I think he did a lot of very nice work on that. Also, we just published a review, for example, in powder technology on that from all the work what has been done until now. I think it's important for dry milling in such ball mills. Then he said, okay, now let's try what we did for wet milling, use this simple equation for the stress energy, knowing that it probably doesn't work, but first have a try. In this case, he wanted to produce a 20 micron for the X90. And so he looked for the specific energy, and then he plotted the specific energy as function of this term. And you see that it's not a nice curve, the points are all around. So that doesn't work. Now the question why. So there can be two reasons. And one reason is that the stress energy maybe is not really defined by this equation. And the other one is that we have a certain mass between the balls or the beads. And this mass changes with the size of the beads and also maybe the flowability of the product and so on. So to achieve now the stress energy, he was running DEM simulations so that we get this speed of the contact speed, the stressing speed correct. And then he also ran some tests in a model device to get a certain knowledge about how much material is captured by the balls. So he runs his DEM simulations using EDEM in this case. We did a really good, let's say, parameter calibration, so that I think the results should be more or less correct. Also, the power draw was very close to the experimental one. And then he calculated, for example, also the density distribution of for the stress energy distribution, showing that for the vertical stirred media mill, there are differences depending on the grinding aid, and that the normal and tangential stress indices are very similar. In ball mills, it was different. So if we calculated for a bigger ball mill with 2 meter diameter, we have much higher stress energies in this case, and also we have differences between tangential and normal direction. But what is most important is that he was now looking for the contact velocity of the beads and how this depends on the stereotip speed, and he found that it's a complex correlation, and this depends also on the grinding media size and the grinding media density. So it's not so simple that this is proportional to the tip speed, independent on the type of the balls. So then he used this more complex knowledge, and also he did experiments to estimate what is a captured mass here with a flat plate in the ball, but he also did it with 2 balls at the end. Because a reviewer said that, and it was a really good idea. And we found that we can now describe this mass. We had this tablets and could really measure the mass of the tablets. We found that the correlation from Schönert is really working good. And we extended this correlation a little bit, like shown here. So it's very similar. We have another parameter K. So we have this alpha. So this angle is a little bit calculated in a little bit different way, like Schönert was saying. But other than that, it's very similar to the one of Schönert. And by that, we now could calculate what is the mass between the balls. And then we can calculate the stress intensity, knowing the correct stress energy and know the correct mass, what is between the balls. And if we do that, then you see that we get nice curves. So that is the newest plots out of his PhD thesis, what I got a few weeks ago. You see that they really fit nicely for the two different grinding aids. And what is also can be seen that depending on the grinding aid, we have a different minimum specific energy. So in this case, for the heptanic acid with a lower, higher flowability, we get a lower specific energy in the minimum than for the other one. And also the optimum stress energy depends then on the flowability of the product, because the mass between the product changes. And so we have a little bit smaller value for the one here than in this case. Okay, yeah. Small volumes, more efficient energy transfer, exactly here in heptanic acid. So conclusion is I could hopefully show you that the stress model can be used to design mills and milling processes. I also used it, for example, for consultancy, designing a mixer. So they also had problems by scaling the mixer, and then I used my model for getting the new bigger mixers, and at the end it worked out really nicely. They were really pleased with that. So I think it's a good strategy. Then the stress energy distribution and energy transfer factor are very important. We should know that for the different mills, and I think we also at least work on determining that for different mills now. I have shown you that impact mills and also dry ball mills are, I think, can be described well by this model if we choose the right parameters. And we can use this model at the end, what I've shown you for the wet stirred medium, really nicely also for predict optimum operating conditions. Yeah. So what we are doing now is DM simulations of different mills, to get this energy, stress energy distributions. And I think in the future, hopefully, we can also do more work on how much material is captured in different mills between the grinding tools. Yeah, then thank you very much for your attention. And thank you very much for all my, the people who are giving the money for the financial support. And especially thank you very much for the PhD students and also the postdocs who are doing most of the work, especially Sandra and Paul. And thank you very much for your attention. So that was almost in time. Yes.
That's great. Thank you, Arno. I think it really brings to our attention. Yeah, well done. I think it really brings to our attention that you can take a fundamental understanding and put it into application, which is overlooked with a lot of the general mineral processing, which if you hadn't met Arno before, you'd understand why I was really impressed with his work and wish to bring it up from the fine to where we work. So do we have some questions for Arno? You basically unmute and ask.
Maybe I should open the chat. I don't have that.
Yeah, but Java, did you want to ask a question? I see you unmuted. Or Aubrey.
Yeah, I have a question. Arno, how does the stress intensity energy curve shift with the media size? For instance, if you use the smallest media, which does not match the feed, and we know that it will not be efficient in grinding, is there a shift that can tell you that the media size that you've chosen is inefficient for this particular application?
Yes, sure. Then you are normally on the left side, of the, let's say, I don't know. Then you are on the left side, of this optimum. maybe I go to this result here. Now then you are here somewhere, you know, and you know, you are not efficient to break the particles, you know, like energy utilization, you know, you are not on the point that in most of the stress events you really break the particle, you know, you maybe achieve some small failures in the particle already, but it's not a really breakage, you know, and that normally if you do have to do that several times, then you lose energy, or, you know, dissipate energy, and you don't get very fast a good result. Yeah. So it's always the best point is really to hit the particle once with the energy where it just breaks, you know, and then if you want to go finer, then take, you know the exact energy what you need for the fragments that they just break, you know, and so on, you know. So that would be the optimum. You know? I mean, it's not, you can't do it usually in a normal mill, but that would be maybe from the thinking, you know, if you want to go to better processes or better mill designs, then that would be how to do that.
Thank you.
So one thing we have in mineral processing is a really wide size distribution coming in. And then you need a whole lot of different stress intensities. I think that's a distinct challenge, and you have a system that's got a distribution. And
yes, right. I think that's what I just mentioned. If you come to this point, then we need a population balance, you know, to calculate that. So what Greta Fangier has done, unfortunately, up to now, I don't have her PhD thesis. She coupled, you know, the distribution, you know, like, you know, I have shown here in principle somewhere here at the beginning, a long way, and coupled it with a population balance. And then, you know, it gets more complicated, right? But at the end, you can come to a correct result. And I think you don't need the entire curve. I think it's maybe good enough to have maybe some sectors, you know, of the stress energy to get a good result. And I mean, what we found, you know, with the mean stress energy already, or that the question is then maybe what we have to cut, you know, what is the stress energies maybe which are not important, where we should cut it, and then calculate the mean. That's also something that we just discussed a lot, also discussed with Anderson, Chagas, you know, how to do that, or what is the best way to do it. Then you get a mean what is really meaningful, let's say, and what you can use then also, you know, to get a certain distribution, because what we found is that, you know, the distribution, what I have shown, depends on the stress energy, you know. But this is then by calibrating the population balance, you know, that, you know, by which mean stress energy you get which distribution. All you need to, if you want to do it really correct, then you need the distribution itself. Yeah. But for optimizing, very often, you know, you know, simpler solutions maybe work, you know.
Okay, Majala, you had a question?
Yeah, first of all, thank you very much, Arno. Very interesting talk. Good summary of the work. In your earlier slides, you refer to the importance of stressing mode, that is impact, compression, and shear. And I just wonder how you differentiate in your calculation of the mean specific energy. How do you actually differentiate between these modes? Because for a given mill, you could actually change the relative contribution of say, shear and compression.
Yeah, that's a good, very good question. So let's say in the, you know, for the normal application of the simple model, I would say, you know, we say it's included both, you know, we don't distinguish between shear and normal stress. Now, if we use DM simulations, then we can really get, you know, the parts, you know, what is a normal distribution, normal stress, what is tangential stress. What I have shown you at the end for the dry milling, you know, for the ball mill, there was a difference between tangential and, well, shear and normal stress. And for the ball, for the stirred media mill. For the dry one, there was almost no difference. And that always, what we found is that also with planetary bore mills, we have done that we get a better correlation if we use, in this case, only the normal part, and not use the tangent, the shear part. That's what I can say. So that was the reason why then we used only the normal stress to calculate at the end the behavior of the mill. But there's a small, also the small part is really pure shear, but shear is more I get to have a mixing and a delocation of the particles in a dry milling process. In a wet milling, it's even more complicated. I think it's both then, because if you have an agglomerate, then shear might be already sufficient. Yeah, then it's getting more complicated.
Thank you. Thank you.
Who else is brave enough to ask a question? I'm sure Marcelo's warming up.
Yes. Thanks, Malcolm. Well, actually, it was not a seminar; it was a master class there from 35 years or so, 30 years of work. Fantastic. Yeah, of course, I would have quite a few points, but at least one I think it would be worthwhile mentioning, which is, could you actually just elaborate a bit more why the issue of mass capture ended up appearing towards the end of your presentation only in dry milling, and you could kind of get away with that without having to worry too much when you deal with wet milling? I anticipate, of course, it's the whole issue of fluidity and bed formation, and the fact that you're actually in wet grinding, you could assume for simplicity that you're stressing almost individual particles. But could you elaborate a bit more on how this mass capture, because you put it as an outlook, as a piece of the puzzle that you will invest more effort in the future, as we have been, because we see exactly the same type of trend.
Yeah, exactly. I mean, Marcelo, you're also working on that very intensively. When we started the work with the wet stirred media mills, we found that for at least particle sizes above 1 micron, that it's independent on the size of the beads. So then from that, I concluded, okay, it seems to be that the active volume between the beads seems to have no role. It's maybe more a little bit on what is the right word? The probability maybe that the particle is catched by the beads, but not how much particles are really catched or caught, not catched, caught by the bead. So, and I think it's, we also, some simulations, when two beads are approaching, fluid is displaced, and then at the end, only in the middle are really 1 or 2 particles which are really stressed. So, but if the solids concentration is very high, or the particles are getting smaller, then this changes, and so that's why Sandra now for really high concentrated suspensions also said, okay, we have to include this solids concentration, because there are more than 1 particle stressed, and then it has to be considered. But still, that is a good question. But I still, for example, I was expecting that with nanomilling, we also have to consider somehow how many, what is the volume between the beads. But it turned out that we don't need that, maybe because it's more a rolling. So, that the beads are roll above each other, what we also can see in simulations. And then it's, 1 particle, the next and the next. So I think it's not solved fully in the moment, but that's what we see in wet milling, that if we have an impact or an contact, that the first particle, what is catched, and that are single particles that get most of the energy. There might be some others who get some energy, but it seems to be not important for the overall result. But if we go to dry milling, it's a total different story. You have really a bed usually between the particles, and so this bed needs to be known. That means we have to find some model equations how to calculate this the mass in the bed.
Arno, actually, some while ago, we did some calculation, DM calculation of the number of particles when two balls collide. And there is a maximum number of particles which they get engaged with themselves and with the surface. And if you increase it more, then they just fly over without getting stressed, without getting engaged with the surface of the balls. And I just wonder whether that mechanism, that is different between wet milling and dry milling.
Absolutely, that is absolutely different, yeah. Did you publish that?
No, we did that one as part of a piece of work for British Nuclear Fuel Limited on some sort of ceramics. And then time passed. We can publish it now, but it's just that there's no time anymore.
But sure, that is absolutely different for that's because also we had a look for wet and dry, so that changes absolutely, yeah. And also the rotation of the beads will be much higher in case of wet milling than of dry milling.
That's interesting. Everyone talks about a stirred mill as a shearing environment, an assumption of their shear, and here you successfully model it only with compression.
Yeah, that's right. I mean,
normal. I think it's quite a wake-up call for how people talk about it, because I've always been wary of this. It's all shear and sliding happening there. The little particle doesn't know that. It's just these two big balls squashing it. So I think it should inform our thinking about how these processes really work. It's much deeper than just the equations, and the outcomes inform one of your understanding. Well, we've gone a few minutes over. I think that's been really interesting, and appreciate you putting so much effort in, Arno, to condense 25 years into 45 minutes. And I think those are really interested, should be inspired. You've given the references, just look up Arno Kwade, download his 87 papers, and you're away. Go to his masterclass next year. You give one every year, don't you, in Germany?
I wanted to do, but we have only a few participants up to now, so we just decided to skip it. I wanted to do it international. There was also one Australian who was saying he wants to join the course, but no, because I think 6 or 7 or 8 were applying, so I said, and because there's a lot of work, to change it from a normal course to a web course, and so the next week would be very busy otherwise. So sort of only a small participants, he said, okay, we then postpone it to next year. Yeah.
Okay, so next year you can be inspired to join Arno's course and really understand. So thank you very much, Arno, and I hope everyone's enjoyed the next GCC seminar, upgrade our intellect and our understanding of the process. And we hope to see you in a month's time again. Cheers.
Thank you very much.
Thank you. Thank you all. Thank you very much. Oh, by the way, before you go away, I just want to make a point in connection with the publication out of ESCC. We haven't received many papers, and the deadline was end of this month. So I think we have something like 5 papers, which I'm processing now. We were expecting something around 30, 40 papers. So I'm just thinking maybe I should extend it by a month, but beyond that, I think is not reasonable. I'm not sure whether how the technology will accept it. So do you see it is worth extending it?
Yeah, we are working on 5 papers here. They are nearly finished, but it's very hard to chase up people under the pandemic. A month will help. Thank you. Maybe end of October will help. Thank you very much.
Wonderful. Okay, thank you. Thank you very much. Yes, bye.
Bye.
Bye, everyone. Thank you.